this axis. So the torque, if we look from above, the torque will be along in the direction of the precession. So maybe the like tangential direction at each point. And then for L, this will be along the axis of the rotor away from the pivot point. So if this is the pivot point, then L will be directing this way. So this is torque, this is L, which will be away from the pivot point, and it will be along the axis of the rotor. So the rotor is spinning like this, so that means the axis is this way. So that's why L will be away from the pivot point. Thank you.
Welcome to Spring LIB.
So in this problem, angular momentum will be conserved. So in terms of rotational motion, we can write angular momentum as I times omega. And since we have two different scenarios, one is when the star is massive, and then the other scenario is when the star is collapsed. So we can denote them into two different entities. So one, let's say when the star is massive, the moment of inertia is I1, and the angular velocity corresponding to that is omega1. So from the conservation of angular momentum, we can set that equal to I2 times omega2, where I2 is the angular moment of inertia when the star is collapsed. Similarly, omega2 is the angular velocity at that time. And we know for a solid sphere, I is 2 over 5 mr squared. Now we have R1 for I1 and R2 will be for I2. So we can write 2 over 5 m R1 squared here, which is equal to 2 over 5 m R2 squared times omega2. So we can get rid of this part, and then we'll have omega2, which we need to figure out, which is equal to omega1 times R1 by R2 squared. And here omega1 is given as 1 rotation per 30 days. So we convert that to radians. So we'll have 2 pi radians divided by 30 days. We convert that to seconds. So that's going to be 86,400 seconds per day times R1 is 7 times 10 to the power 5 kilometers, and R2 is 16 kilometers. Then we take a square, so that gives us finally 4.6 times 10 to the power 3 radians per second. Thank you.
Welcome to Spring LIB.
So here's a top view of the setup. Here we see that the bar is pivoted at this end, and the bug sits here, and this is the table. So the bug jumps off perpendicular to the pivot point. We say this is the direction, and there are a few notations that we should remember. Now we're saying that A is defined as bug, like A as defined as the object bug, and B for the bar. So MB corresponds to the mass of the bar. Similarly, MA corresponds to the mass of the bug. And when the bug jumps this way, then there will be some angular speed or angular velocity on the opposite direction, and we mark that as omega b. Now, also we're given the length of the bar, which we call r here. So if we apply conservation of angular momentum here, we see that before collision, the angular momentum is zero because the system was at rest. But after the bug jumps, there will be some non-zero angular momentum, and we can calculate that using this expression, where ma times va is the linear momentum, and we multiply that by the radial vector, so that gives us the angular momentum. Since omega b is going in the opposite direction, so we put a negative sign after that, and then we put the angular momentum due to the pivot or due to the bar, which is ib times omega b, where ib is the moment of inertia for the bar. Now we see that since the bar is pivoted at one end, so ib will be 1/3 mbr squared. So from here, we'll equate these two things, before collision and after collision. And since this part is zero, so this whole thing should be equal to L1, which is equal to zero. So from there, we get omega b equals to 3ma va divided by mbr. So all we did here is we substituted IB by this expression and then solved for omega b. And using the given values, so we're already given MA, MB, R, and VA. So using the given values, we see omega b is 0.12 radians per second. So to review, omega b is the angular velocity after the bug jumps from the bar. So in part B, we need to find out the kinetic energy of the system. So before the bug jumps, the system was at rest, so the initial kinetic energy was zero. But the final kinetic energy will be the kinetic energy due to the bug jumping off. So the linear velocity of the bug is VA. So half mv squared is the kinetic energy of due to the bug jumps at a certain velocity. Then we have the rotational kinetic energy. This is because the bar starts rotating, which is half of IB times omega b squared. And we have already shown how to get IB and omega b. We already got omega b from the previous part. So if we put all the numbers, we see that the kinetic energy is 3.2 times 10 to the power minus 4 joules. And in part C, the source of energy is basically when the bug jumps, it pushes the bar, and because it pushes the bar, there is some work done by the bug on the system, and that work done is been converted to the kinetic energy. Thank you.
Welcome to Spring LIB.
So we're told that an airplane propeller has a tip-to-tip length of 2.08 meters, and it weighs 117 kilograms. And it applies, initially at least, it applies a torque of 1,950 newton meters. The engine does to the propeller. Now, we're going to assume that the propeller is just a rigid bar rotating about its center. So the mass moment for that is 1/12 ml squared. And so that we know that the initial torque equals the mass moment times the initial acceleration. So the initial acceleration is 12 times the initial torque over ml squared. Plugging everything in, we get that is 46.2 radians per second. Now, we're asked to, what is their angular speed after 5 revolutions? Well, we can use our kinematic relationship that the final velocity squared, the final angular velocity squared is the initial angular velocity squared plus 2 times the acceleration and over the angle that that acceleration acted. And again, we're assuming that this is a constant acceleration. Initial speed we were told was 0. So the final speed is the square root of 2 times alpha naught times the change in angle. The change in angle we're told is 5 revolutions, but that's 10 pi radians. So plugging everything into here, we get the final angular velocity is 53.9 radians per second. And then we'll ask how much work is done by the engine during this first 5 revolutions. Well, the work is just the torque times the angle of rotation. And again, assuming this torque is always constant, I guess we call that T naught. Assuming that we have a constant torque over the whole range, that's simply just 1,950 times the angle, which is 10 pi, or that winds up being 61.3 kilojoules. Now they ask, what is the average power output during the first 5 revolutions? Well, we need to figure out, to get the power, average power, we need to figure out how long it took to get up to this speed here, or how long it took to go through 5 revolutions. So delta t equals the change in angular velocity divided by the angular acceleration. And again, this is assumed to be constant. This is 0, so we wind up with 1.17 seconds. So it took 1.17 seconds to go through 5 revolutions. I'm not sure if I did 5 or 6 there, but anyway. So now that we know the time it took, we can say, well, here we have the work that was produced, or the work that was put into the propeller over that time. So divided by the time gives us an average power. And that average power winds up being 52.4 kilowatts. They then ask us at the instant, what is the instantaneous power after it is turned through 5 revolutions? So that means that we have the instantaneous power is the torque, which we know, I assume it's still this value, and the final velocity, which we know. So that's just that. And plugging all those in, we get 105 kilowatts. So we can see it's almost about double what the average is. And 500 and
I just have to put in -3 in the numerator.
The power starts off at
Welcome to Solar Fire, the place where learning becomes simple.
I just
If
have
you
to put
struggling with
in
homework assignment,
-3
doubt in subject, don't worry. You are in the
Type
right to Solar Fire, the
negative
place where learning
and,
So the
becomes
world gets
simple.
about
If you struggling
80% of
with
its
homework
energy
assignment,
from
-3
doubt in
broad
subject,
group of
don't
chemicals
worry.
we
You are
call
in the
fossil
right to
fuels.
Solar
It's
Fire.
everything from, so the world gets about
If you
80% of its
struggling
oil,
with
petroleum,
doubt in
broad
subject,
group of
don't worry.
just
You are in the
fossil
right to
fuels,
Solar
carbon,
Fire.
everything from, so the world gets about 80% oil, petroleum,
Doubt in
broad
subject,
group,
don't worry.
just
You are in the
fossil
right to
fuels,
Solar
carbon,
Fire.
everything from, so the world gets about 80% oil, petroleum,
Doubt in
broad
subject,
group,
don't worry.
just
You are in the
fossil
right to
fuels,
Solar
carbon,
Fire.
everything from, so the world gets about 80% oil, petroleum, broad group, just fossil fuels, carbon, everything from, so the world gets about 80% oil, petroleum, broad group, just fossil fuels, carbon, everything from, so the world gets about 80% oil, petroleum, broad group, just fossil fuels, carbon, everything from, so the world gets about 80% oil, petroleum, broad group, just fossil fuels, carbon, everything from, so the world gets about 80% oil, petroleum, broad group, just fossil fuels, carbon, everything from, so the world gets about 80% oil, Bye.